All right, today we are diving deep into an incredible story. It's about cosmic collisions and the permanent, almost secret clues they leave behind. This is Deep Impact, the science of shock.
I mean, just try to wrap your head around that for a second. An impact so powerful, it literally reshapes a planet in an instant. It unleashes pressures and temperatures so extreme, they're almost beyond our imagination. So, what could possibly survive that to tell the tale? Well, believe it or not, the only witnesses are the rocks. They become the forensic evidence of this cosmic crime scene. They're permanently scarred, they're transformed by the event, and if you know how to read them, they can tell you exactly what went down millions of years ago. So to start our investigation, we've got to go to the scene of the crime. We're talking about places like Meteor Crater in Arizona, a massive, gaping scar on the planet left by an impact 50,000 years ago. It's in places like this that scientists first started to piece this whole cosmic detective story together. This entire field, this whole detective story, it really hinges on one key process. It's called shock metamorphism. You can think of it as the collection of unique fingerprints that a shock wave leaves behind. And we're not just talking about simple cracks and fractures, no. These are fundamental changes to the very atomic structure of minerals. Okay, so what do these fingerprints actually look like? Well, to find them, we have to zoom way in, go microscopic, and reveal these telltale signs of an impact that you just don't find anywhere else on Earth. For example, take a super common mineral like feldspar. It starts out as a totally normal, orderly crystalline mineral, but you hit it with a shock of about 20 to 30 gigapascals. That's hundreds of thousands of times the air pressure around you right now. And its beautiful, orderly structure just collapses into a disordered glass called masculinite. It's like a ghost of the original crystal. And quartz, another mineral that's pretty much everywhere, gives us even more clues. A powerful enough shock can turn it into a unique glass, kind of like the feldspar. But it can also do something even weirder. It can force the atoms to rearrange themselves into an incredibly dense, high-pressure crystal called stishovite, a mineral that should only exist deep, deep inside a planet's mantle. Now, if you really want to understand the sheer, raw power we're talking about, just look at graphite. You know, the soft carbon in your pencil? Well, an extreme impact, we're talking over 170 gigapascals, can instantly transform it into lonsdaleite. That's a rare, super hard, hexagonal diamond found only in meteorite impact sites. Yeah, from pencil lead to a diamond in a flash. So finding these clues out in the field is one thing, but to really, truly understand them, we have to try and recreate these cosmic impacts right here on Earth. So welcome to the Crime Lab. Scientists use these massive gas guns to fire projectiles at tiny rock samples at just incredible speeds. It's a way to generate a controlled, high-pressure shockwave in a lab. Then, after the blast, they carefully collect what's left to see what transformations happened, and they compare those lab results to what we find out in nature. And after thousands of these experiments, scientists have developed what's essentially a shock barometer. It's amazing. They can look at a specific mineral transformation and basically read the pressure of the original impact. See some microscopic cracks in quartz? Okay, that was about 5 to 20 GPa. Find some lonsdaleite? Whoa, you're looking at an event that blew past 170 GPa. Every single fingerprint tells us about the intensity of the blast. Analyzing the aftermath is incredibly powerful, but modern tech is letting us do something that is truly mind-bending. We can now watch these transformations happen not in the days or years after, but in the nanoseconds during the impact itself. This is really the cutting edge. Using these unbelievably powerful X-ray lasers, scientists can basically take snapshots of a mineral's atomic structure as the shock wave is passing right through it. It's like having a super slow motion camera, but for atoms. So when scientists did this with quartz, they saw something absolutely amazing. The shock wave hits. Just 10 nanoseconds later, boom, that high-pressure stishovite forms. But then, only 20 nanoseconds after that, as the pressure wave passes, the stishovite just collapses into a disordered glass. This means that some of these impact minerals might only exist for a fleeting moment before they become the evidence we find millions of years later. And watching this in real time led to a huge discovery. It turns out the pressure needed to create that shocked glass is actually 25% lower than we thought. And why? Well, because it's easier for the quartz to quickly become that fleeting stishovite first, which then turns to glass, than it is to just force the quartz straight into glass. Our whole understanding of these events is changing. right now.
So how does all this microscopic detective work, both in the field and in the lab, build up to the bigger picture? Well, it allows us to read these epic, incredible stories that are written in stone all across our solar system.
It really comes down to this. The physics that unfolds in a billionth of a second inside a lab is the exact same physics that carved out those massive craters on the moon and on Mars. It's a universal language, and it's written in minerals. So why does all this matter? I mean, who cares? Well, because understanding these shock waves helps us piece together how planets themselves were formed in the first place. It allows us to better assess the risk of future impacts right here on Earth. This knowledge is even used for things like optimizing mining, and it tests these profound theories, like whether life could survive being blasted from one planet to another. The applications are they're truly vast.
So the next time you see a picture of a crater on the moon, or you hear about a meteorite, remember this. The real story isn't just the hole in the ground. It's in the silent, transformed witnesses, the rocks themselves. They hold the secrets of a violent cosmic past, and by learning their language, well, we might just get a little better at preparing for our own future.